All right, here's what we got today. We are, for the rest of the semester, we got two more units. We got waves and sound, and then light. We'll call that good for the year. I did want to, there was a couple things that I wanted to tell you about with electromagnetic waves that we ran out of time. Okay, is wirelessly charging. So the docking station, whatever, has a coil wire that has changing current, alternating current that creates a changing magnetic field. Your phone also has a coil wire similar to a transformer. It is in this changing magnetic field and induces a current which charges your battery. Good with that? Okay. The second thing is the tap technology on a credit card. So your credit card has actually a coil wire embedded in it. Like there's a transparent credit card, and the device that reads it has a coil wire that has a changing current in it that creates a changing magnetic field that induces a current in here, powers the chip. Your chip has a specific encrypted code that your reader, the card reader, can verify. Connect that to your bank or credit card account. Okay. Downside to this, is that other people, bad guys, can get one of these card readers and come up to you and, like, if you're close enough, can like read your card through your wallet or purse. So, just in general, the more convenient your life is, probably the more susceptible you are to being hacked. Okay, so like it's really nice being able to start your vehicle from inside to get your vehicle warmed up on a cold day. But that also has potential for someone to like intercept that and from another place and like out. I'm sure they're working really hard to try to prevent that, but know that that's as convenient as things increase in convenience. There's also more risks. So, throwing that out there. This is an X-ray of the chip itself, so you can kind of see how it's wired. The security part of that is in the center here.
Well, how did they get things that small to be that precise?
They get way smaller than that.
I know they do it for LEDs, but how? How do you do it by hand, which is literally thousands of times bigger?
You don't do it by hand. Robot makes it.
Of course, robots that make more robots.
All right. So, waves. So, by the end of this lesson, you'll be able to identify parts of a wave, calculate the speed of the wave, identify different types of waves. Okay. Hey. Wave. This is a traveling disturbance through medium carries energy. Traveling disturbance through a medium that carries energy. Okay. Medium. This is the material through which a wave travels. Material through which a wave travels.
There's even sound in space. You can tell in your vacuum.
So think of a
Yes.
football stadium wave. What is the medium?
People.
People. Okay. Do the people travel? No. But they're just disturbed. Sitting there and like, ah! Right? And energy carried, we'll just say the hype is carried. Good with that? Okay. All right. Traveling disturbance through a medium that carries energy. Medium is material through which the wave travels. Some of this stuff you might have learned already in math class or another science class. Wavelength, no, amplitude.
Also something you learn in
This
calculus.
is the distance from the undisturbed medium. So that's your amplitude. That's your amplitude. Undisturbed medium, let's say you had a pond. Still pond, that's your undisturbed medium. You throw a rock in that pond and it makes ripples or waves. How far it is away from that original, that's your amplitude.
Sound travels faster in more dense environments.
Okay? We will get there. So it's a distance, so we're measuring this in meters. Wavelength, this is the length of one complete cycle. Okay. The variable for that is lambda and upside down y. I don't know why. Upside down, backwards, lowercase y. Lambda. Okay. Might have seen that in chemistry last year. Okay. And the unit for that, it's a length as well. So this is also in meters. So amplitude and wavelength are both in meters.
Using those small. They use metrics instead of imperial.
Okay. Have a conversation.
Why am I hearing this?
But HC can't be the amplitude. That's
Oh,
your
no,
IC.
it's IC.
I see that.
Yeah.
HI is amplitude, right?
Let me see. Was it the sign period or something?
Yeah, I think it's only like half of it.
Segment is
No, remember, because like that's what you restrict it to if it's gonna be a function. Remember?
Oh, I think it's B, right? I think it's B. B. B.
Actually,
Come on.
now I'm scared it could be.
Correct answer is
B. B.
boy. Correct answer is E.
I knew it.
Such
Why are we second guessing?
Okay.
God.
Such a jerk. He throws none of these on the first
There's no such thing as
question. Okay. Wavelength could be A to E, B to F, C to G, one complete cycle. Amplitude could be I to H or I to C. Good? What?
Wavelengths could be I2.
I to H for amplitude. Oh. You could do. I'd rather. You could go I to whatever. C to G.
Okay, thank you.
Okay. All right. So these are all distance-based measurements, amplitude and wavelength. These are time-based. Okay. So period is the time for one complete cycle. Talked about this with circular motion. Okay. The variable for that is capital T, and the unit is seconds. Time for one complete cycle. Okay. Frequency, this is how many cycles per second. Turns out that frequency is equal to the inverse of the period. So 1 over the period is equal to the frequency. So cycles per second is the unit. Which is equal to a hertz, like the rental car company. Yeah, cycles per second is hertz. Now, with this insight, the unit for frequency is cycles per second. You could say that the unit for period is seconds per cycle.
Period in seconds per cycle. Frequency is cycle is inverted.
Okay, do that.
Tangent and arctangent. Or cotangent.
Tell your neighbor what you think. Correct answer is. There we go, there. Okay. So you want the period, so you want seconds over cycles. The frequency would be what? Frequency would be 4 cycles per second. 4 hertz. Good with that? Okay. There will be a test question just like this. Okay? Both on this test and on the final. Statistically, a third of you are going to miss it. Sad, because it's not a hard question. Okay? I'm not trying to trick you. Okay? I'd really love it if you were on the 2/3 side of that. Okay? The key is you look at your units. Okay, we'll try it again. Tell your neighbor what you think.
Yeah.
Eight.
Correct answer is A, cycles per second. You want 12 cycles, 4 cycles over 12 seconds. And the period would be 3 seconds. Good with that? Okay, not a hard question. Make sure you get the easy points. All right. Speed. What in math class, algebra class, so what's the equation for speed? Distance over time. Okay, it still holds true. Distance over time.
Speed of sound on Earth is 343 meters per second.
Yep, we'll get there
That's
next
Mach
week.
1, really.
Okay. Talking about waves. What is the distance for one complete cycle?
Wavelength?
Wavelength. What is the time for one complete cycle? Period. Wavelength over period also gives us the speed of the wave. And since we know that frequency is equal to the inverse of the period, we can also say this. Frequency times wavelength is equal to the speed of the wave. All 3 of those equations are valid for the speed of the wave. Distance the wave travels in a certain amount of time, the wavelength of the period, and frequency times the wavelength. You actually have done this in chemistry. You did last year, you did C is equal to frequency times wavelength. That was because you were dealing with an electromagnetic wave that moves the speed of light. In case that isn't in there, we'll swing back around and hit that. Okay? Good? your neighbor.
Oh. Oh.
What's your first name?
Correct answer is
B.
B.
Hey.
Okay. We're going to take the wavelength divided by the period. Amplitude is a distractor. The amplitude does not mess with it. The speed of the wave is independent of the amplitude. Good?
You do realize these are white capital waves.
Huh?
They're big. I've seen those on Lake Michigan. They're bad enough. Imagine them screaming 60s.
Probably need a calculator on this one.
Oh God. What? Oh. What? Yeah.
Tell your neighbor.
Oh geez.
What you do?
Divided by thousand.
B, I think. Sorry.
Oh, I'm looking for
B,
the
right?
frequency, but
How is it that big? Hold on. That's like over 1,000 times most of the other answers.
I think it's B.
What?
I think B too.
Correct answer is
B.
E.
Of course.
What's the answer?
Is it 1450?
Everything's like 1,000 times.
1,450 meters a second. You could either
No.
do distance over time. You could do wavelength over the period. You could do the wavelength times the frequency.
It's still the same result.
Is 1,450 meters per second.
Yes. B is basically 1,000 times less.
Okay? You do that?
So this is inside of water.
Yep.
What about in a solid? Wood.
We'll get there. All right. There are two different types of waves that we're going to look at. One is a transverse. This is when particles in medium oscillate perpendicular to the way the wave travels. Particles in a wave, bless you, and the medium oscillate perpendicular to the wave wave travels. So oscillate is the scientific word for moves back and forth. You guys ever heard of an oscillating tool like in construction? It goes back and forth really fast. Soft stuff to cut stuff. Okay. So, what does it mean when the particle in a medium oscillates perpendicular to the way the wave travels? Pick a dot. Well, first off, which way is this wave traveling? It's going to the right. Ready? Good at that. So pick a dot and see how the dot is moving back and forth. This might help you.
Not helping. It's not helping me.
Okay. Yeah, it's oscillating back and up and down while the wave travels that way. It's oscillating perpendicular to the way the wave is traveling.
Why you get pushed by waves is because of gravity.
Good. And transverse wave. Okay. So there's just another. Okay. Second type is a longitudinal wave.
Basically the same thing, but from above.
So what this looks at is instead of oscillating perpendicular, it oscillates parallel to the way the wave is moving. So in the animation, the waves are moving to the right. But if you pick a single particle, it's just moving back and forth. Look at that. Longitude. So just another demonstration of that. Good.
But can you make it?
Okay. So a football stadium wave, would that be a transverse or longitudinal wave?
Transverse.
Be transverse. The disturbance is "Whoa," as the wave goes sideways. Good? Okay. To draw a longitudinal wave is challenging. So, actually, before I do that, there's some parts of the wave, some vocabulary. This part is known as compression, which that's not mind blowing. The spread apart parts are known as rarefaction. That's the weird word. Okay. So a lot of times what we'll do is we'll draw a longitudinal wave as a transverse wave, but graphing it as pressure. So this would be normal pressure, would be your undisturbed medium, and then this would be high pressure, higher pressure, and this would be a low pressure.
Essentially, a probe. but
Okay.
above the main line.
Good with that? A lot easier to draw that pressure graph than it is a bunch of dots. Good there? So a water wave is actually a combination of transverse and longitudinal happening at the same time. Okay? If you think of your experience at Lake Michigan or at the ocean, watching something float, whether it's like a buoy or a seagull or a piece of driftwood, it doesn't just do this. Okay? Or if you've ever been snorkeling, if you're near the surface, it's like whoa, whoa. And not only is it up and down, but it's also that way. And as you get deeper, it's not as crazy. Good? Okay. So, interference. This is when multiple waves overlap. We'll get to superposition here momentarily. What I have here is the world's longest slinky.
Same thing makes ferrets go crazy.
Okay. What we're going to do is sorry. Help me.
Yeah.
Okay. Stand pen over here. Okay, get so where you can see this. What I want you to do is you're gonna go to your right like that and make a big fold. So go fast like there you go. Okay, so I'm gonna go the same way. What you're gonna do is you're gonna observe what happens when the waves overlap each other. Ready, set, go. Ready, set, go. Ready, set, go. Okay. Now we're going to do the same thing, but I'm going to go the opposite way. Ready, set, go. Ready, set, go. Okay. One question, another question I have is, do the waves bounce off each other or pass through each other? Ready, set, go. Ready, set, go. What do you see? Bounce off or pass through? Pass through. Okay, good with that? So we'll do it same time or same way and then opposite. Ready, set, go. Same, opposite, ready, set, go. Okay. Good. Thank you, sir. So what you just observed was interference. So this is known as constructive interference. when they're going the same way. Okay? So here they come together and like whoop. So the superposition part happens to figure out the total amplitude. Okay? So here, what we have is at this moment in time, we have an amplitude of +2. On this one, at that same moment in time, we have an amplitude also of +2. So the total amplitude, the superposition of it, is going to be +4. Adding those together. Okay? They don't have to be like the same. Like here we have 2, and here we have 1. So at that moment in time, we have 3. That's constructive interference. They're going in the same. The amplitudes are in the same direction. Destructive interference is when they're going in opposite directions. Notice this, you can see how they're passing through each other a lot easier. Bit of that. Okay. So this would be an extreme example of destructive interference, where you have an amplitude of +2 here, -2 here. Adding those together, the superposition of that is 0. Okay. They don't have to cancel all the way out to be destructive interference. We could look at this point here. So this is like 1.8, and this would be like -1.2, 1.3, we'll say. And so this gives us +0.5. That would also still be destructive interference. Good? Good? You gotta read a pre-quiz for Monday, I apologize. You gotta get a roll. Good?
It's also sound wave space, but they're just another form of energy that can be translated.